All right, so we left off with the idea that Erwin Schrödinger developed what we refer to as quantum numbers for, or wave equations that described quantum numbers for the location of electrons surrounding the atoms. The lining up of these three quantum numbers, okay, so the combination of the three quantum numbers describe what we refer to as orbitals, and how much energy is associated with an electron in that orbital. So each orbital that gets described has some type of a spatial distribution surrounding the atom. So it's essentially a three-dimensional location. So when Bohr talked about the atoms, about the electrons in the atom, he talked about the electrons orbiting the atom, like they were on a path and they were moving. The orbitals, I wish we had used a different word so it sounded a little different, but orbitals are essentially three-dimensional regions where the electrons are located. It's probably better if you think of them more like they're like balloons that surround the nucleus. And they can be different sizes and different shapes, all right? But they encompass a three-dimensional region around the nucleus of the atom. Each one of those is what we refer to as an orbital, and it's defined by three different numbers that come out of the Schrödinger wave equation. What I'm really interested in you understanding is the physical meaning of these three different parameters that we're going to talk about, okay? So the principal quantum number is the first one. I'm just going to kind of pull this down so you can see the bottom of the screen. So the principal quantum number is given the symbol n, and what it does is it describes the energy level in which the orbital resides. So one of the ways we typically think about this is as the size of it. So the size of the electron, of the orbital. So this principal quantum number gives me some idea about how big the orbital is where the electron is located. How far away from the nucleus does it expand? And as the value of n gets bigger, and n can be any integer, anything greater than 1, okay, so like 1, 2, 3, like that. So as n gets bigger, the electron that essentially is located further away from the nucleus. We can also calculate the maximum number of electrons in any principal energy level using the equation that says that it's equal to 2 times n squared. So if I'm in the second energy level, if n equals 2, 2n squared is 8. If I'm in the third energy level, 2n squared, oops, that should say 2n squared, I just noticed. 2n squared, oops. 2n squared would be equal to 18. So 2 times 3 squared is 9, times 2 is 18. The second quantum number we're going to talk about defines the shape of the orbital. So the orbitals are going to differ based on size and shape. And the numerical values that accompany this, what we refer to as the angular momentum quantum number, and we give it the symbol L. These are integers again, and they range from 0 to n minus 1. So we also give them letters. So the letters that we use, the S, P, D, and F that you see down at the bottom here are the way that we typically refer to these. So each of these numbers or letters designates a different shape of the orbital. So I can have an orbital that's in the first energy level, and it has this S shape. And then I can also have an orbital that's in the second energy level, and it also has this S shape. Now my orbitals can only hold 2 electrons. So I'm going to need a lot of orbitals. I have to describe a lot of orbitals in order to place my electrons. The last value we have is what's referred to as the magnetic quantum number. So the magnetic quantum number, we give it the symbol m sub L. And this defines an orientation. So one way to think about this is, if I think about my orbital, let's say that it's shaped like a pencil, all right? So it's shaped like a cylinder. Then my orbital could be pointing up and down. It could be the same size and shape, but it could be pointing horizontally, or it could be pointing essentially in the z direction. So this orientation would indicate that they're mathematically equivalent. They have the same size, the same shape, but they have a different orientation in space. So these have values that go from minus L to plus L. So for instance, so I'm going to try and show you this. And it's not the numbers as much as how many values that you're interested in. So if L equals 0, this is what we kind of refer to as an S-shaped orbital. The only value for M sub L is 0. So there's only one possible value. When L is equal to 1, so if I move over to L is equal to 1, now I have 3 different values that M sub L can take. When L is equal to 2, works out to be 5 different values that ML can take. And then when I move over to L equals 3, I have 7 different values that it can take. So there's 7 different orientations when L is equal to 3, or essentially what we refer to as an F-shaped orbital. Now I know this is confusing. What I usually find is that once we start actually using this information, it's going to make a little more sense to you. So I thought first we'd kind of look at some shapes and what these orbitals, essentially, how can we picture these orbitals, okay? So let's talk about S-shaped orbitals. So the value of L for S-shaped orbitals is 0, all right? When we say they're S-shaped, they're actually shaped like spheres. So as the radius of the sphere gets bigger, then the principal energy level gets bigger. So I'm showing you a picture here of a 1s, a 2s, and a 3s orbital. You see they're all shaped the same because they all have that s. Their size is increasing. So the 1s is the smallest, the 2s would extend further from the nucleus, and the 3s would extend even further from the nucleus. So let's take a look at the next slide here. So this picture is trying to show you how these orbitals essentially are nested together. So these Schrödinger wave equations describe what we refer to as the probability of where you're most likely to find an electron. And what you can see is I would have my 1s orbital at the bottom. This would be my smallest orbital down at the bottom. Oops, I changed my slide again. Grab my pen again. So my 1s orbital down here at the bottom. All right, it's a radius of a sphere that surrounds the nucleus, and it shows you here where this blue line is the highest. That's where I'm most likely to find an electron. Then my 2s orbital is essentially nested around that, and the place where I'm most likely to find my electron is a little further away. And then my 3s orbital is essentially nested around that as well. So we can think of the electrons as being in any of these orbitals. And don't forget, we don't just have S-shaped orbitals. We also have P-shaped orbitals. So this is what our P-shaped orbitals look like. So the value of L for a P-shaped orbital is 1. So these kind of look like, I always think of these like a three-dimensional infinity sign or dumbbells, all right? So they have 2 lobes, and they kind of right at the center where those axes are crossing, that's where my nucleus would be located, okay? And these are our D-shaped orbitals. So D-shaped orbitals, the value of L is 2. There's 5 of these. They kind of look like three-dimensional clover leaves. The center, again, is at the nucleus. The last one looks quite a bit different. It doesn't really look like the others at all. It looks more like a P-shaped orbital with a donut around the center of it, but it's mathematically equivalent. So when we start talking about this as being a shape, sort of starts to fall apart a little bit there because the shapes start to look a little bit different, but they are mathematically equivalent. And I don't have pictures of the F-shaped orbitals, but they kind of look like a cluster of Easter eggs is the way I always think about them. So the question is, what are we going to do with all this? All right, so what our goal is to take the electrons that we have surrounding an element and to place them into these orbitals. All right, and so the orbitals have a hierarchy of energy that it takes to get into each one of them. And some of them require more energy than others, and some of them are at the same amount of energy as others. So we're going to look at this. This is what we refer to as an Aufbau energy chart. So I'm showing you this chart, and you probably want to pause and fill in. There's arrows in each one of these little boxes. So this is going to be what we call an Aufbau energy chart for the element sulfur. So sulfur has 16 electrons, and we're going to use arrows. We're going to use these up or down pointing arrows to represent the electrons. And we're going to use these rectangles or squares to represent an orbital. So what this chart is showing you is the orbitals from lowest up to highest energy up at the top, all right? And we're going up as far as a 4p orbital right now. So any place where you see more than one orbital, so like right here, there's more than one orbital that's at the same amount of energy. Those are called degenerate orbitals. And it takes the same amount of energy to get into each one of those. And together, those orbitals make up what we refer to as a sublevel. So this would be a sublevel. So what we do essentially is we take our electrons. We have 16 electrons. We start down at the bottom and we put 2 electrons into each orbital. So I start by putting 2 electrons into the 1s box. So what I'm trying to draw there, I didn't have a lot of space, is an up arrow and a down arrow, because as the 2 electrons go into the orbital, they actually have what we refer to as a different magnetic orientation, meaning the way that people usually visualize this is as they spin in different directions. So one of my electrons would be spinning one way, my other one would be spinning in the opposite way. So I put my first 2 electrons in that lowest point, and then I move up to my next orbital. So my next orbital I can put electrons in is my 2s orbital. So I put 2 electrons in there. And my 2p orbitals, I fill those, my 3s, and my 3p. I can end with my 3p. Now when I go to put the electrons in the 3p orbitals, I don't pair up electrons until I have to. So what I would do is I would put 1 electron in each of those 3 boxes, then I would go back and pair them up if I have to. All right. So it's requires less energy for an atom to exist with all of its electrons spinning the same way than if they have to be paired up. And so the electrons go in one at a time. So what I want you to do, so what we want to do then is we want to take and write these sublevels and say how many electrons are in each one. So what I've done over here is I listed the sublevel, so the 1s, we started with the 1s, and this little superscript is telling me how many electrons are in that sublevel. Then I listed the 2s, and I said, okay, there's 2 electrons in there. The 2p has a total of 6. The 3s has 2, and the 3p has 4. This is what we refer to as a complete electron configuration. Okay? So what I'd like you to try and do is there's another Aufbau chart for another element here. I want you to try and fill in another one of these before you look at it. I lied. There's not another one there. All right, I'm sorry. So when we write electron configurations, what we're going to do is show the distribution of all of the electrons in an atom, and we show them by sublevel. So when I write these little values that I'm writing, all right, and I list the sublevel, the number, that's the energy level. The letter is the shape or the type of orbital, and the superscript is the number of electrons in that entire sublevel. So that's how I write them. There's another quantum number that we haven't talked about yet. So the last quantum number is referred to as the spin number. And I think that what I'm going to do is I'm going to pause the video. I'm going to stop the video here, and I'll finish this up in the last slide because this might take a little while to explain.